Projectile motion is a branch of classical mechanics in which the motion of an object or projectile is analyzed under the influence of the constant acceleration of gravity after it has been propelled with some initial velocity.
Aristotle lived around 400 BC. He believed that the rate at which an object falls was directly related to its mass. Unfortunately, he was wrong. He believed that an external force is needed to maintain the motion of an object, and also suggested that air rushes around the moving object and pushes it forward. Once again, he was wrong.
Galileo, who lived during the 16th to 17th century, was a hugely influential astronomer, physicist, and philosopher. His findings disproved Aristotle's beliefs to be incorrect about projectile motion. Galileo's first theorem, which is a projectile which is carried by a uniform horizontal motion compounded with a naturally accelerated vertical motion, describes a path which is a semi-parabola.
I'm going to drop these two balls, and as you see, they will hit the ground at the same time. So, ready? Same time.
Same time.
Example of projectile motion.
Here is another example of projectile motion.
This is projectile motion because it's a projectile only being acted upon by the force of gravity. Alright, let's go.
So due to projectile motion, this basketball and this golf ball will drop at the same time. Ready? Alright, as you can see here, we have a ramp measured by increments of 20 centimeters that has a inclined angle at 5 degrees. Then there's a drop off of 76.5 centimeters, leading to a board that measures in centimeters how far the ball travels in distance.
Okay, so just come in, so you say it, and then you also.
Go. This is projectile motion. As the ball increases in velocity,
Go 4 people, 30 minutes.
as the more distance the ball travels.
Can only have how many got over here?
Go ahead.
20.
Should click on it. There you go.
like 25. It's like 35. 40. It's like 43.
What about like
That's the same
can you
one.
projectile?
Doesn't have that.
Where now?
He's the one with the gun.
What we're doing here is we're trying to find the velocity of the ball by measuring the time and by increasing the distance from 20, 40, 60, all the way up to 200 centimeters. So what we do, we just drop it, we measure from the front, there to there.
Because we need to go to the house.
Now we are finding the velocity of the soccer ball by measuring the time in seconds from the distance to 0. From 40, from 60, from 80, from 100, from 120, from 140, from 160, 180, and 200.
Our basic setup is a ball on a 5-degree angle ramp, which rolls down accelerating until it gets to the horizontal surface of the table, where the velocity remains the same until it hits the ground. Go.
Alright, to go over how we collected our data, we used these two equations, which are pretty much modified versions of this kinematic equation. Our dx, our dependent variable, our vx, our independent variable, is horizontal velocity, which changes the distance in centimeters of which the ball lands. And our t is the amount of time it takes from the ball, from the table surface to the bottom surface. And we use this equation, square root of 2 dy over the gravitational force of negative 9.8 meters per second squared.
Here we have our collected data. In the first column is the height in centimeters we released the balls on the ramp. The second is the time it took to get to the end, and the third is the velocity at the end of the table. The fourth is the distance that it traveled on the ground. To the right of the data are the two force diagrams. The top is showing the forces during acceleration on the ramp, and the bottom is showing forces during the free fall after it falls off.
This line graph shows how far the ball went, and on the y-axis is the velocity, centimeters per second. On the x-axis is the distance in centimeters. Thank you for watching our video.